Hey everyone, welcome back for another deep dive. If you're out there getting ready for, your next big step in software engineering, thinking about those, especially those challenging senior software engineer technical interviews, and
Oh, yeah?
this one's for you. Today, we are going to really explore a design pattern
Okay.
that can really showcase your understanding of how to build like really robust systems,
Yeah.
really well-structured systems.
Yeah.
We're talking about the composite pattern.
The composite pattern, absolutely. This is one that, it's not just about knowing another pattern off the list. It's about showing that you can think about, like, how do you handle complexity in a really elegant way?
Yeah.
How do you, signal to an interviewer that you understand, object-oriented design and you can speak that language? And that's what this pattern is all about.
So let's unpack this a bit. Imagine you're designing a system
Okay.
where, you have things that are made up of smaller parts.
Right.
And those parts can even be made up of even tinier pieces. Right. Think about like building a complex UI or managing a really nested configuration file or something like that.
Yeah.
The composite pattern is a way to organize these objects into a tree-like structure.
Right. Sure.
And what's really powerful about it is that it allows you to treat both the individual components and the larger groupings of those components kind of like in the same way consistently.
Yeah, that's key. That consistency, that uniformity across the board, whether you're dealing with one little tiny element or like a whole assembly of elements, right? You can interact with them the same way. The operations are the same.
Right.
And that can just like dramatically simplify how you deal with like these really complex structures in your code.
That's it. So for me, like the aha moment with the composite pattern, right? Like I'm reading about this and it finally clicks and it's like, wow, this is all about reducing the complexity for the client code, right?
Yeah.
Like you don't have to write a bunch of, special case logic to handle individual items versus collections of items.
Right.
You interact with everything through a common interface.
Yeah.
Right. It's this idea of like, treat these all the same, even if under the hood, some are simple and some are, quite intricate.
That's it. And, that simplification really translates directly into code that's much easier to understand, to maintain, to modify, to extend, right?
Yeah.
More flexible.
Yeah.
And these are all like the hallmarks of like well-engineered systems.
So in our deep dive, we are going to look at the fundamental definition. Like, what is it?
Oh,
Why would you even use this thing?
Sure.
How's it structured?
Right.
What are the roles of the different players involved? We've got the component, the leaf, the composite, the client.
The whole gang's here.
Whole gang's here. Where is this pattern most applicable? What are the benefits? Are there any drawbacks? There's always got to be a trade-off, right?
Yeah.
Of course.
We'll look at considerations for when you're actually implementing this.
Right.
We'll walk through an example, a concrete example with equipment.
Yeah.
We'll discuss its use cases in the real world. So we'll look at some examples with GUI frameworks and compilers.
That's good.
And finally, we'll even explore how it relates to other design patterns that you should know, especially for moving into that senior role.
This is a deep dive for sure.
Yes.
And, it's designed to give you like a really solid understanding of this pattern.
Yeah.
So that you can not just know it, but you can articulate it, you can communicate it, you can explain it, you can discuss it, and really show your interviewer that you understand it deeply.
So let's start with the core,
okay.
Right? What is the composite pattern in essence?
Yeah.
And can we maybe think of an analogy that would be helpful to really grasp it? At its core, the composite pattern is all about organizing objects into tree structures, right? So you can represent part-whole relationships.
Okay.
The key, though, is that it lets you treat both individual objects and these whole compositions in the same way uniformly.
Okay.
So think about like navigating a file system on your computer, right?
Okay.
You've got files, which are individual items, and then you've got folders, which can contain other folders or files. And when you do something like list the contents or calculate the size, you're kind of doing it the same way, whether you're dealing with a file or a whole directory.
Right.
So the directory acts like this composite that contains other components, which could be files or other directories, and the files themselves are like the leaves.
Okay, so I see that. So the file system is like the whole structure.
Yeah.
The directories are like the composite nodes,
right,
and then the files are like the leaf nodes. And we can perform similar actions on both.
Yep.
Now, let's go back to that key phrase. Individual objects and compositions uniformly.
Yeah. Yeah.
How does that manifest in our file system analogy?
It means that you can do something like, get size on a single file, which just gives you the size of that file.
Right.
Or you can do get size on a directory.
Yeah.
And it will like recursively calculate the total size of all the files and subdirectories in it.
Right.
And the code that's asking for the size doesn't even need to know if it's a file or a directory. It just uses the same interface.
So it's like saying, hey, item.
Yeah.
Tell me your size.
Yeah.
And the item knows whether it's a single file that just reports its size or a directory that has to like go ask all of its little,
It's children.
Yeah, it's children for their sizes and add them up.
Exactly.
I got it.
And that's what makes the composite pattern so powerful for dealing with these like really complex hierarchies.
Right.
Now, let's break down the structure of this pattern a little bit and talk about the roles of each of the main players.
Okay, so we have this thing called the component.
Right.
What's its responsibility in all of this?
So the component is like this abstract interface that defines the common operations that both individual objects, like the leaves, and the composite objects need to support. It's like the contract for everything in the tree.
Okay.
These operations could include things like, getting a name, getting some information about it.
Right.
And then, importantly, operations that can be applied to like the whole structure, like our get size example, or maybe in a UI, it might be render or something like that. The component might even define default behavior for things like adding a component, removing a component, or accessing children.
Right.
Even though those operations might not make sense for leaf nodes.
So it's kind of like setting the stage for how all of the elements in this hierarchy will behave.
That's a good way to put it. It gives you that consistent interface that everyone's going to use.
Right.
Then you've got your leaf objects.
Right.
What do they do?
Well, these are like the fundamental building blocks, right? The individual objects that don't have any children.
Right.
So like in our file system analogy, that's a specific file.
Exactly.
And it implements the operations defined in the component interface.
That's right. A file has a name. It has a size. It can be read. But it can't contain other file system nodes. So it's just this concrete implementation of the component interface for a single entity.
Okay. And then we've got the composite itself.
Right.
What does it do?
So the composite, like our directory example, is a container.
Okay.
So it holds a bunch of child components.
Okay.
And those could be other composites or they could be leaves. Right, like subdirectories.
Yeah, like subdirectories, exactly.
Got it.
And it implements the things you need to manage those children.
Okay.
Like add a child, remove a child, get a child.
Yeah.
It also implements those operations from the component interface.
Okay.
But it often does that by like delegating down to its children.
Okay.
So when you ask a directory for its size, it goes through all of its children, asks them for their sizes, and adds them up.
So the directory has this list of like file system node components. Right. And when you call get size on the directory, it goes through that list. Yeah. And it calls get size on each item in the list, whether that item is another directory or a file.
Exactly.
So it's that recursive nature of it.
It is. It is.
Got it. Okay. And then finally, we have the client.
Yes.
What's the client doing with all of this?
So the client is the code that actually uses this whole composite structure.
And the beauty of it is that the client just talks to the structure through the component interface.
Okay.
It doesn't need to know if it's talking to a file or a complex directory tree.
Right.
It just says, hey, give me the size or render yourself or whatever.
Yeah.
And the pattern takes care of all that complexity underneath.
Yeah, and that is a crucial point, right?
It is.
Like if you're going into a technical interview talking about the composite pattern, like highlight the fact that the client doesn't have to know about that underlying structure.
It makes the code much more loosely coupled.
Yeah.
Much more flexible.
Yeah, absolutely. So let's talk about the why behind this pattern, right?
Sure.
What problem is the composite pattern really trying to solve?
So the main motivation here is when you have these hierarchical structures and you don't want to treat individual objects differently from containers that hold them. Right. Without this pattern, you'd end up with all this conditional logic in your client code to handle each type separately. imagine building a UI without this pattern.
Yeah.
You'd have different code paths for rendering a button versus a panel that has a bunch of buttons on it. Right? It would just get really messy.
Yeah, you might have like a render button function. And a render panel function. And the render panel would have to
do about everything inside.
Yeah. And call their individual render functions. Oh, that sounds...
It would get really, really complicated.
Yeah, very complicated, very quick.
Especially with nesting.
Yeah, especially with nesting.
So the composite pattern solves this by having this common render operation on like a base UI component. And then buttons and panels and everything, just implement that.
So then the client code can just call render.
Exactly.
And it doesn't care if it's rendering one button or the whole window with all the stuff in it.
The whole application. Yeah.
Okay, so the applicability is really when you're modeling these like part-whole relationships. And you need a way to interact with the parts and the wholes in the same way.
That's it.
Okay. Now, let's think about the consequences of using this pattern. What are the benefits, right? And are there any trade-offs that we need to think about?
So benefits, first of all, it gives you a really clear hierarchy between your leaves, like your individual objects, and your composites. So the whole structure of your system is much more organized, easier to understand. Second, and we talked about this, it simplifies your client code a lot. The client doesn't need to know all the concrete types. It's just using the interface. And that makes it much more adaptable if you need to change things later.
More maintainable.
Much more maintainable, exactly. What else? It also makes it much easier to extend your system. So you can add new types of components, whether they're leaves or composites, without breaking your client code. As long as they follow the component interface, you're good to go.
So like introducing a new type of UI control or a new kind of container shouldn't break the existing functionality.
Exactly. As long as it implements those necessary operations, it's all good.
From the component interface. Got it. Okay, so those are some great benefits. Now, what about trade-offs? Like with all this flexibility, there's got to be like some some things to think about.
One potential downside is that it can be hard to enforce specific constraints on what types of components can be children of a particular composite. So like in our file system, you wouldn't want a file to contain other files, right? But the composite pattern, like structurally, it would allow that. So you might need to add some runtime checks to make sure things are being used correctly.
So it gives you all this flexibility, but you might need to add extra logic to make sure it's like semantically...
to make sure it makes sense for your application.
But for your actual domain.
Exactly.
That's a good point, especially in system design. Okay, so now let's get a little bit more in depth here. For those who are like really prepping for those tough technical interviews, what are some like implementation considerations and trade-offs that we should highlight?
All right, so a few key things to think about during implementation. One is parent references. So sometimes it's helpful for a component to have a reference back up to its parent in the tree. It can make it easier to like walk back up the tree, to delete things, or even to support patterns like the chain of responsibility pattern. But if you're going to do this, you have to be really careful to keep those references up to date whenever you're adding or removing components.
So like when a component is added to a composite, its parent reference needs to be set correctly. And then if it's removed, it needs to be like cleared or updated appropriately.
You got to make sure everyone knows who their parent is.
It's like a family tree.
It is.
Yeah, you got to keep it consistent.
Okay, another key decision is about child management operations. Like add, remove, get child. There's this trade-off between transparency and safety. So if you put these methods in the base component interface, it's transparent, right? You can call them on anything, but it's not very safe because it doesn't make sense to add children to a leaf.
A leaf can't have children.
So you might end up throwing an exception there, like an unsupported operation exception or something.
So transparency means you have like a uniform interface, but some operations might not be valid, and you only find out at runtime. Safety means like a slightly less uniform interface, but you prevent those like nonsensical operations.
You catch them early.
At compile time.
At compile time, exactly.
Got it.
You could also define those operations just on the composite class.
Right.
That's safer type-wise.
Right.
But you lose some transparency because now the interface isn't like totally uniform.
Right.
You need to know if you're dealing with a composite before you try to manage its children.
Okay, that makes sense. So what about maximizing the component interface?
Right.
Like what's the goal there?
The goal is to put as many common operations
Okay.
in the component interface as possible.
Yeah.
So that you can really use that uniform treatment.
Right.
You want the client to be able to do the same things to any component.
Right.
Often the component class might provide default implementations for those operations.
Right.
And then the leaf and composite subclasses can override them if they need to.
Right.
But this can sometimes clash with the idea that a class should only have methods that are meaningful for it.
Right.
Like a method like get child count might only make sense for a composite.
Right.
And having a default implementation in the leaf class that just returns 0, it can feel a little forced.
Right.
So it's a balancing act between having a powerful interface and not putting methods on things that don't need them.
Right, right. So you don't want like interface bloat.
Exactly.
Right. You want to keep it
clean.
Yeah, keep it focused.
Okay, last thing to think about is should the component class itself hold the children?
Okay.
Like, should it have the data structure for the children?
Right.
You might think, put it right in the base class where you have all the add and remove methods.
Yeah. Right.
But that means every single leaf would have that data structure.
Right.
Even though it'll never use it.
Yeah, it doesn't have children.
Right.
Right.
So you could waste a lot of memory that way.
Right.
So it's a trade-off between convenience and memory usage.
Yeah.
You might be okay with it if you don't have many leaves.
Right.
But if you have a lot of leaves,
it
could be a problem.
Right. Okay. That's really helpful, like walking through those implementation details, especially if you're, in a technical interview and you can really talk about that.
For sure.
That shows like a deeper level of understanding.
Absolutely.
Okay, so let's move on to a concrete example.
Okay.
We talked about equipment.
Right.
How does that demonstrate the composite pattern?
So the equipment example is basically you've got individual pieces of hardware, like a floppy disk or a memory stick. Yeah. And then you've got composite pieces of equipment that are made up of other components, like a chassis that holds drives and boards, or a cabinet that holds multiple chassis and power supplies. Yeah. So you've got this base equipment class that defines some common operations, like get power to see how much power it uses, get net price to calculate the price. Okay. And it also has methods for adding and removing sub-equipment, even though those methods might not make sense for individual components.
Right, like a floppy disk, you can't add anything to it.
Right. A floppy disk is just a floppy disk.
Yeah.
So in this example, the floppy disk would be a leaf. Okay. Right? It implements get power, get net price. Yeah. But if you try to add something to it, it might throw an exception. Okay. Now, the composite equipment class, that's our composite. Right. It inherits from equipment, and it has a list of its sub-equipment. And it implements the add and remove operations to manage that list. Okay. The really cool part is how it implements get net price. Yeah. Okay. So it goes through its list of sub-equipment. Yeah. And it calls get net price on each one. Right. Whether it's another composite like a chassis or a leaf like a floppy disk. Right. And it adds up the prices.
And that's the uniform treatment, right? Like the code that's calculating the total price. Yeah. Doesn't need to know.
Doesn't care.
Yeah, doesn't care.
What type it is.
What type it is.
Exactly.
It just asks for the price and adds it up.
That's the beauty of it.
Yeah, I love that.
And then you'd have like concrete composite types like chassis, cabinet, and bus. Right. That would each have their own way of organizing their sub-equipment. Okay. So you've got these different levels of hierarchy.
Right, like the chassis can have stuff in it, the cabinet can have chassis in it, and so on. Okay, that example really makes it like much more concrete. Yeah. So where do we see this pattern used in real-world systems?
Oh, it's everywhere.
Okay.
One of the most common places is GUI frameworks.
Okay.
So think about how you build user interfaces.
Right.
You've got your top-level window.
Yeah.
Then you've got panels inside the window.
Right.
And then you've got buttons and text fields and labels.
Inside the panels.
Inside the panels, yeah.
Right.
So a lot of GUI frameworks use the composite pattern for this. Like the old Smalltalk MVC framework had this view class that could be either a container or a control. And then, more modern frameworks like ET++ and interviews, they use similar ideas.
So like a window can have panels in it. The panels can have buttons and input fields in them. And it all like responds to events and renders on the screen. That makes sense.
What else?
Another big one is compiler frameworks. So when a compiler is like processing code, it often builds this tree structure called an abstract syntax tree, or AST. And the nodes in that tree are often implemented with the composite pattern. So you might have a node that represents like a whole expression, and then it has subnodes for sub-expressions and variables and operators. And those subnodes could be more composites, or they could be leaves.
Like individual tokens.
Exactly. And then the compiler can like walk that tree to do things like semantic analysis and optimization and code generation.
So it provides a consistent way to like process that code.
It does.
Regardless of how complex it is. Okay, very cool.
You also see it in financial modeling.
So
like a portfolio could be a composite of individual assets, like stocks and bonds.
Or even sub-portfolio. And then it can calculate its total value or its overall risk by asking all of its components for their values. And it's even related to the command pattern. So you can have a macro command that's a composite of individual commands.
So it's really cool to see this pattern show up.
It's all over the place.